there is a strange privilege hidden inside the night sky. Every galaxy you can see through a telescope is arriving from the past. Some of that light began its journey before Earth had continents. Some left when the first multicellular life had not yet appeared. Astronomy has always depended on this delay. We do not travel across the universe. The universe sends us its history. That simple fact has encouraged another assumption. If we build larger telescopes, collect more light, and wait long enough, then more of the universe will eventually reveal itself. Knowledge may be slow, but it should keep expanding. Current cosmology suggests something far less reassuring. The observable universe is not simply growing larger. It is also developing boundaries that no future technology can overcome. Entire galaxies are being carried away by the accelerated expansion of space itself. They are not vanishing because they are too faint. They are disappearing because the geometry of the universe is changing faster than their light can continue reaching us. Under the standard cosmological model, there is a horizon beyond which events occurring today can never influence Earth, no matter how advanced our sentience become. A Wikipedia. This is not an engineering problem. It is not a limitation of mirrors, detectors, or radio antennas. It is a consequence of the universe's own evolution. For most of human history, horizons represented temporary ignorance. Sailors crossed oceans. Spacecraft crossed the solar system. Every frontier seemed to invite another expedition. The cosmic horizon is different. It is not waiting to be crossed. It is steadily erasing the possibility. That distinction changes the emotional weight of modern cosmology. We often imagine the future as an era of greater knowledge, where each generation inherits a more complete picture of reality than the last. Yes, if the universe continues expanding at an accelerated rate, the opposite may be true on the largest scales. Future astronomers could possess instruments beyond anything we can imagine while having access to less evidence than we do today. Wikipedia. Think about what that means. Human civilization may exist during one of the rare periods in cosmic history when the evidence needed to reconstruct the universe is still visible. That idea sounds almost backwards. The early universe was hotter, denser, and more violent. One might expect later civilizations to enjoy clearer observations after billions of additional years. Instead, time itself becomes an obstacle. Expansion stretches light until it grows weaker, redder, and eventually impossible to detect. The galaxies are still there. Their histories continue. Their stars continue burning for immense spans of time, but their stories stop reaching us. The first clue that this could happen emerged near the end of the 20th century. Two independent teams, Type Ia supernovae, expected to measure how gravity had slowed cosmic expansion over billions of years. Instead, they found evidence that expansion had begun speeding up. The result pointed toward an unknown component, now called dark energy, incorporated into the standard lambda-CDM cosmological model. Wikipedia. That discovery solved one problem and introduced another. Acceleration means distance is not simply increasing. The rate at which space itself expands changes the long-term relationship between observers. Galaxies that are not gravitationally bound to our local group drift farther away until the light they emit today will never arrive here. Future signals become permanently inaccessible, even though older light already traveling toward us can continue arriving for billions of years. Wikipedia. The universe is not switching off all at once. It is closing doors one by one. Every observation made by modern astronomy exists inside a limited window. The cosmic microwave background, the distribution of distant galaxies, the expansion history encoded in redshift, these are not permanent features available to every civilization across time. They are conditions tied to a particular era. If intelligent observers arise trillions of years from now inside what remains of the Milky Way's merged descendant galaxy, they may see almost nothing beyond their own gravitational neighborhood. The broader universe would have slipped beyond their observable horizon. without distant galaxies, without measurable expansion, without detectable relic radiation from the Big Bang, many of the conclusions we consider foundational could become nearly impossible to derive from observation alone. Wikipedia. That possibility creates an unsettling reversal. We usually measure scientific progress by improved technology. Cosmology reminds us that timing matters just as much. Knowledge depends not only on intelligence but also on what reality still allows us to observe. And recently, another layer of uncertainty has appeared. New analyses from the Dark Energy Spectroscopic Instrument have raised the possibility, still unconfirmed, that dark energy may not behave exactly as the simplest version of the Standard Model predicts. If future observations support this trend, our expectations about the universe's ultimate fate, including the evolution of the cosmic horizon itself, may require revision. For now, researchers emphasize that the evidence is intriguing rather than conclusive. Relighters 4. That uncertainty does not weaken the mystery, it deepens it. Because whether dark energy remains constant or slowly changes, the largest question survives. How much of the universe are we losing while we are still learning how to look? And perhaps more unsettling still, how would we know when the last observable clue has already passed us by? The simplest way to picture a cosmic horizon is to forget about galaxies for a moment and think about a conversation. Imagine speaking to someone while both of you stand on moving walkways. At first, the distance grows slowly. You raise your voice, and the words still arrive. Then the walkways begin accelerating. You speak louder, wait longer, invent better ways to transmit your message. None of it matters. Eventually, the separation increases faster than your words can ever travel. Nothing has happened to your voice. Nothing has happened to the other person. The space between you has become the deciding factor. That is remarkably close to what modern cosmology describes, except the moving walkway is space itself. One of the most common misunderstandings is the idea that galaxies are racing through the universe like bullets. That picture feels intuitive because it resembles motion we experience every day. But it is also misleading. On the largest scales, distant galaxies are not primarily moving through space. The fabric of space between galaxies is expanding, carrying them farther apart. This distinction explains why sufficiently distant galaxies can appear to recede faster than the speed of light without violating Einstein's theory of relativity. Nothing is outrunning light through space. The geometry of space is changing. That sounds like a subtle mathematical correction. Its consequences are anything but subtle. When Edwin Hubble demonstrated that distant galaxies exhibit larger redshifts, the discovery transformed cosmology. The universe was not static. It had a history. Every observation pointed toward expansion from a denser, hotter beginning. For decades, researchers assumed gravity would gradually look at that expansion. Matter attracts matter. Given enough time, the growth of the universe should become increasingly restrained. Then the supernova measurements overturned that expectation. Instead of slowing down, expansion was accelerating. That single observation changed the future as much as it changed the past. Acceleration introduces a limit that did not exist in the earlier picture. Light, leaving certain distant galaxies today, begins a race it cannot win. Every second that signal travels, new space forms along its path. The destination continues retreating. The gap continues widening. The journey never finishes. Those photons still exist. They simply never arrive. This is where the idea becomes difficult to accept emotionally because it collides with one of our deepest assumptions about science. We tend to believe that enough patience can overcome almost any observational challenge. If an object is too far away, wait. If it is too faint, build a larger telescope. If the signal is weak, improve the detector. Astronomy has rewarded that philosophy for centuries. The cosmic horizon is different because patience works against us. Waiting does not reveal more of the universe. Waiting allows more of it to disappear. That realization changes the meaning of every major observatory, on Earth and in space. The Hubble Space Telescope did not simply photograph distant galaxies. It preserved views that future observers may never reproduce under different cosmic conditions. The James Webb Space Telescope is extending that record even farther into the early universe. By detecting infrared light from galaxies formed only a few 100 million years after the Big Bang, it is collecting evidence from an era that later civilizations may never have direct access to, if the observable universe continues shrinking relative to their horizon. Seen this way, astronomy begins to resemble archaeology, not because the universe is dead, because its evidence is temporary. Every survey becomes an act of preservation. Every spectrum becomes a historical document. Every deep field image captures relationships that are slowly dissolving. Now consider another consequence. Our own galaxy is not escaping this future. The Milky Way and the Andromeda Galaxy are expected to merge billions of years from now. Smaller nearby galaxies, bound by gravity, will remain together, forming one enormous system. Inside that merged galaxy, stars will continue forming for a time. Planets may still orbit stable suns. Intelligent life could still exist. From a local perspective, almost nothing would appear unusual. The night sky would still contain stars. Nebulae would still glow. Planets would still circle their suns. Yet beyond that gravitational island, the wider universe would steadily fade from view. The countless galaxies filling today's astronomical catalogs would no longer decorate the sky. Not because they had ceased to exist, because no new light from them could ever arrive. Imagine trying to reconstruct the history of Earth after every fossil older than a few thousand years had vanished. Imagine attempting to discover evolution with no ancient rocks. Imagine searching for continental drift without oceans. The challenge facing those future astronomers would be even greater. Many of the observations supporting modern cosmology depend on structures extending far beyond our local group. Remove those observations, and entirely different theories could appear reasonable. A civilization living trillions of years from now might conclude that its galaxy constitutes the entire universe, not because they failed as scientists, because the evidence available to them would point in that direction. For the first time, ignorance would not result from limited intelligence. It would result from living too late. That possibility forces a remarkable inversion of perspective. We often picture ourselves as arriving early, equipped with primitive instruments and incomplete theories. Cosmology suggests something else. In at least one respect, we may already be late, but not yet too late. The window remains open. The question is how long it stays that way, and whether we have understood what we are seeing before it quietly closes. If future astronomers could lose access to the evidence that shaped modern cosmology, an uncomfortable question follows almost immediately. How certain are we that our own picture of the universe is complete? History offers very little encouragement, again and again. Scientific revolutions have begun with observations that looked almost insignificant at first. Mercury refused to follow Newton's equations perfectly. Tiny irregularities in starlight revealed that the universe was expanding. Slight fluctuations in the cosmic microwave background eventually became a map of every galaxy that would later exist. The clues were always there. What changed was our ability to recognize them before they disappeared beneath more comfortable explanations. The cosmic horizon may represent another version of that challenge, not because it hides the truth, because it limits how much truth remains available. Every observation in astronomy is an exercise in reconstruction. We never watch an entire process unfold. Instead, we collect fragments arriving from different distances and therefore different moments in time. Nearby galaxies appear older. Extremely distant galaxies reveal the universe in its infancy. Massive galaxy clusters expose billions of years of gravitational evolution. The night sky is less like a photograph than an archive assembled from chapters written across nearly 14 billion years. That archive only works because enough chapters remain accessible simultaneously. Suppose those chapters gradually disappear. Suppose every galaxy beyond the local group eventually fades beyond detection. Could anyone still discover the Big Bang? At first, the answer seems obvious: yes. After all, the stars would still exist. Matter would still behave according to the same physical laws. But the evidence supporting the Big Bang is remarkably interconnected. One pillar comes from the expansion of distant galaxies. Another comes from the microwave background, the faint radiation left behind when the universe became transparent, roughly 380,000 years after the Big Bang. A third comes from the observed abundance of light elements, such as hydrogen and helium, matching predictions from primordial nucleosynthesis. Each line of evidence strengthens the others. Remove enough of them, and confidence weakens. Eventually, an entirely different interpretation may become the most reasonable conclusion available. This possibility has fascinated cosmologists because it reveals something unusual about scientific knowledge. Science depends on evidence. Evidence depends on observation. Observation depends on where and when you exist. That final condition is easy to overlook because human history occupies such a tiny fraction of cosmic time. Civilization has advanced over only a few thousand years, while the universe has evolved for nearly 14 billion. Against that backdrop, our era feels almost instantaneous. Yet that instant may coincide with one of the richest observational periods any intelligent species could experience. The cosmic microwave background still fills the sky, although only detectable with sensed instruments. Galaxies remain visible across enormous distances. The large-scale structure of the universe has not yet slipped beyond observation. Expansion remains measurable. These facts seem ordinary because they define the universe we inherited. They may instead represent a brief observational opportunity. There is another way to appreciate the scale of that opportunity. Imagine opening a history book whose earliest chapters slowly erase themselves each year. The newest pages remain untouched. The oldest become increasingly incomplete. Eventually, entire civilizations vanish from the record. Future readers might never suspect those missing chapters existed. Astronomy faces a similar challenge, except the missing pages are written across billions of light years. The archive edits itself, not intentionally, not violently, simply through the continued expansion of space. This changes how we think about observatories. When astronomers point powerful telescopes toward the deepest reaches of the universe, they are not merely searching for spectacular images. They are preserving information that future generations may never be able to recover independently. Every deep survey becomes more than a scientific project. It becomes assist against cosmological time. That perspective also is one of the most celebrated achievements of recent years. The James Webb Space Telescope was designed to observe some of the earliest galaxies ever formed. Its discoveries have revealed systems that appear surprisingly mature for such an early stage of cosmic history, prompting vigorous discussion about how rapidly galaxies assembled after the Big Bang. Most of these findings remain consistent with cosmology after continued analysis, though several have encouraged researchers to refine models of galaxy formation rather than abandon them altogether. Notice what makes those observations valuable. Not simply that they are distant. They preserve evidence from an era no laboratory could ever recreate. Every photon collected by Webb began its journey before Earth had oceans filled with complex life. Those photons survived billions of years, only to arrive during the lifetime of one technological civilization, ours. There is no guarantee another civilization will receive the same record. The more carefully you examine that coincidence, the harder it becomes to dismiss. It does not suggest humanity occupies a privileged place in the universe. It suggests we occupy a privileged moment within one specific kind of observation. Those are very different claims. One elevates humanity, the other elevates timing. And timing, unlike destiny, can expire. If that window eventually closes, future observers may inherit extraordinary intelligence, extraordinary technology, and extraordinary patience, while lacking the one resource that cannot be rebuilt. Evidence that has already crossed the horizon forever. The idea that we may live during a uniquely favorable era for cosmology carries an uncomfortable implication. It means the universe itself may be easier to understand today than it will be in the distant future. That sounds almost impossible. We usually imagine knowledge moving in one direction. Every generation inherits larger telescopes, faster computers, and more refined theories. Scientific mistakes are corrected. Blind spots become opportunities. Progress seems irreversible. On human timescales, that picture is largely true. On cosmological timescales, it becomes incomplete. There are discoveries that require not only intelligence, but access to evidence that still exists. Once that evidence disappears, no amount of reasoning can fully replace it. Consider how we learned that the universe began in a hot, dense state. No scientist witnessed the Big Bang. Instead, researchers assembled independent clues that all pointed toward the same conclusion. Galaxies were receding from one another. The abundance of hydrogen and helium matched predictions from nuclear physics. The cosmic microwave background filled the sky with a nearly uniform glow left over from an earlier epoch. Large-scale galaxy surveys revealed patterns that grew naturally from tiny density fluctuations measured in that ancient radiation. Each clue supported the others. Remove one, and the picture becomes weaker. Remove several, and alternative explanations become increasingly plausible. Now imagine an observer living 100 trillion years from now. The local group has merged into a single giant galaxy. Almost every external galaxy has crossed the cosmic event horizon. The expansion of the universe is no longer measurable because there are no distant galaxies left to compare against. The cosmic microwave background has stretched to wavelengths so enormous and energies so weak that detecting it becomes effectively impossible, even with technology far beyond ours. The relic radiation has not vanished. It has simply become inaccessible. To those future observers, the universe would appear remarkably static. They could study stars. They could develop quantum mechanics. They could discover general relativity. They might even understand nuclear fusion and black holes with extraordinary precision. Yet, the observational foundation for modern cosmology would be gone. Ironically, they might possess better physics than we do, while holding a far poorer map of the universe. This thought experiment is not merely philosophical. Several cosmologists have explored exactly this possibility, because it reveals an important boundary between physical law and scientific inference. The laws of nature do not guarantee that every truth remains permanently observable. Sometimes reality preserves its history only temporarily. After that, the record begins to erase itself. This distinction changes how we think about evidence. We often assume evidence accumulates indefinitely. Libraries grow, databases expand, measurements become more precise. Nature is under no obligation to behave the same way. Some observations are non-renewable. The light arriving from an extremely distant galaxy tonight can never be replaced. Once that galaxy's newly emitted light falls permanently beyond our horizon, there is no second archive waiting somewhere else. No hidden backup. Every photon collected by an observatory is part of a finite historical record. The universe continues producing light. It does not continue delivering all of it. That difference is subtle. It may also define the limits of future knowledge. There is another consequence that reaches even deeper. Much of modern physics assumes that sufficiently advanced civilizations could eventually solve almost any scientific mystery, given enough time. The cosmic horizon quietly challenges that optimism. Time is not always an ally. Sometimes it is the mechanism that removes the evidence before the question is answered. This does not mean science is fragile. It means science is historical. Every theory reflects both the intelligence of its observers and the universe those observers were able to measure. Had humanity evolved billions of years earlier, we would have faced different unanswered questions. Billions of years later, we would inherit different missing evidence. Neither civilization would necessarily be more intelligent. Each would simply occupy a different chapter in the observable history of reality. That realization also changes how we should view today's great observatories: the Hubble Space Telescope, the James Webb Space Telescope, ground-based facilities such as the Very Large Telescope and the upcoming Extremely Large Telescope. They are often described machines for discovering new objects. That description is incomplete. They are preserving relationships that will never exist again from our point of view. Every redshift measurement, every gravitational lens, every distant supernova, every faint galaxy at the edge of detection. Together they form something larger than a catalog. They form a historical record of a universe that is gradually becoming less observable. And perhaps that is the most unexpected consequence of the cosmic horizon. The tragedy is not that the universe is disappearing. The tragedy is that its disappearance is almost perfectly silent. No explosion announces another lost galaxy. No warning appears across the night sky. No observer notices the exact moment when one more region of the universe slips beyond every possible future conversation. It simply happens, again and again. Until one day, long after humanity is gone, an intelligent civilization may look into the darkness and sincerely conclude that their lone galaxy is all that has ever existed. Not because they ignored the evidence, because the evidence had already left. There is a temptation to end the story here. The universe is expanding. The horizon is growing. Galaxies are slipping away. The conclusion appears obvious. We are watching the observable universe slowly shrink. But that picture leaves out the most difficult question of all. Why is any of this happening? For nearly 3 decades, the leading explanation has been something we cannot directly see, isolate, or reproduce in a laboratory: dark energy. The name sounds as though it describes a substance. In reality, it is a label for an observation. The equations describing the expansion of the universe require an additional component that behaves unlike ordinary matter or radiation. Instead of slowing expansion through gravity, this component drives accelerated expansion on the largest scales. Beyond that, certainty begins to fade. Researchers can describe how dark energy influences cosmic evolution with remarkable precision. Explaining what dark energy actually is has proven far more difficult. One possibility is that it reflects the energy of empty space itself, a cosmological constant, an idea Einstein once introduced into his equations, before later abandoning it. In the modern Standard Model, that constant fits an enormous amount of observational evidence with impressive success. Yet it introduces one of the deepest mismatches in theoretical physics. When physicists estimate the energy of the quantum vacuum, using conventional quantum field theory, the predicted value exceeds the observed cosmological constant by an almost unimaginable margin. Depending on the calculation, the discrepancy approaches 120 orders of magnitude. Nothing else in modern physics comes close. It is not a small disagreement. It is the largest known mismatch between theory and observation. For decades, that contradiction has remained unresolved. The standard cosmological model continues to work extraordinarily well, despite the fact that one of its central ingredients lacks a satisfying physical explanation. That is an unusual situation. Normally, successful theories become stronger as their foundations become clearer. Here, the opposite has happened. The observations continue improving. The underlying cause remains elusive. This is where the cosmic horizon acquires an entirely different meaning. It is easy to think of the horizon as something that limits future civilizations. it also limits us. Every attempt to understand dark energy depends on observations extending across immense distances and billions of years of cosmic history. Astronomers compare galaxies at different epochs, measure subtle patterns in large-scale structure, observe distant supernovae, and trace the ACE evolution of expansion itself. Those measurements are possible because the observable universe still contains enough accessible history. The horizon is not merely hiding distant galaxies. It is gradually removing the laboratory in which cosmology is performed. That realization becomes even more significant when considering recent observations. Data from projects such as the Dark Energy Spectroscopic Instrument have prompted careful discussion about whether dark energy behaves exactly like a cosmological constant or changes slightly over cosmic time. At present, the evidence is not strong enough to overturn the standard model, and independent observations will be needed before any revision can be accepted. That caution matters. Scientific history is filled with intriguing anomalies that disappeared after better measurements. It is equally filled with small discrepancies that eventually transformed entire fields. Today, no one can honestly say which category these new results belong to. That uncertainty is not a weakness of science. It is one of its defining strengths. Cosmology advances by resisting the urge to treat incomplete evidence as certainty, yet uncertainty carries its own existential weight. Suppose dark energy never changes. The observable universe continues contracting toward isolated gravitational islands. Suppose dark energy evolves in unexpected ways. Then our picture of the distant future may itself require revision. Either possibility leaves us confronting the same reality. The largest experiment ever available to intelligent observers is unfolding only once. Unlike laboratory physics, we cannot restart the universe under different initial conditions. There is no second trial, no control sample, no alternate universe against which to compare today's observations. Everything cosmologists infer about the evolution of reality comes from one expected universe observed during one finite period of its history. That limitation rarely receives the attention it deserves. When we hear about billion-dollar observatories or increasingly sophisticated simulations, it is natural to assume that humanity's greatest obstacle is technological. Sometimes it is. But at the largest scales, technology cannot manufacture evidence that no longer reaches us. The universe determines what remains observable. Science determines how we will interpret it before it disappears. That distinction may define the future of cosmology, not because we are approaching the end of discovery. Quite the opposite. Every improvement in our instruments increases the urgency of understanding the evidence that still survives. The night sky has always appeared permanent. Its deeper structure is anything but. Behind the familiar stars, beyond the galaxies visible in every deep field image, the observable universe is quietly changing shape. Not through vice, not through catastrophe, through the ordinary operation of physical law. And if physical law continues exactly as our best models suggest, then somewhere beyond the limits of today's telescopes, another region of the universe has already crossed a boundary from which no future light will ever reach us. No observer noticed. No signal marked the moment. The conversation simply ended. There is an instinct that has followed humanity for as long as we have looked upward. We assume the universe is there to be discovered. Every generation inherits questions, builds better instruments, and leaves behind a slightly clearer picture than the one it received. That rhythm has become so familiar that it feels almost inevitable. The cosmic horizon asks us to consider something far less comfortable. Perhaps discovery is not an unlimited resource. Perhaps it has seasons. Not because the laws of physics change, but because the evidence available to intelligent observers changes with time. That possibility transforms our relationship with the night sky. When we look at a deep field image containing thousands of galaxies, we are not simply looking across distance. We are looking at a collection that no future observer may ever see in its entirety again. Every faint point of light represents information still reaching us during an unusually favorable chapter in cosmic history. The universe is allowing us one glimpse, not because it was designed that way, because by chance, we exist while the archive is still open. This idea can easily be misunderstood. It does not make humanity cosmically important. The universe has no indication that it cares whether anyone is watching. Galaxies merged for billions of years before Earth existed. Dark energy began shaping cosmic expansion long before the first living cell appeared. The horizon will continue growing, long after every trace of human civilization has disappeared. Nothing about this process depends on us, and yet our existence intersects with it in a remarkable way. We happen to live during the interval when the universe still contains enough observable evidence to reveal much of its own history. That is not a privilege granted by nature. It is an accident of timing. Accidents can be temporary. This realization quietly changes the meaning of astronomy itself. Astronomy is often described as the study of distant objects. Perhaps it is better understood as the preservation of disappearing information. Every spectrum collected today may become impossible to reproduce. Every precise redshift measurement becomes part of a historical record that later civilizations may never verify independently. Every improvement in sensitivity captures photons that have spent billions of years crossing an expanding universe, only to arrive during one narrow observational window. Those photons will never make the same journey again. Their successors are already being carried beyond reach. The night sky, then, is not a permanent library. It is a library whose oldest shelves are so slowly being removed while we are still reading. That perspective also changes how we think about ignorance. There is ignorance born from a lack of curiosity. There is ignorance born from inadequate technology, and there is another kind altogether. Ignorance created because reality itself no longer preserves the evidence. Future observers may be every bit as intelligent as we are. They may possess mathematics beyond our imagination and technologies that make today's observatories appear primitive. None of that guarantees access to observations that have already slipped beyond the cosmic horizon. Knowledge is constrained not only by intellect, but by opportunity. Opportunity has a lifetime. Perhaps that is the deepest implication of accelerated expansion. It does not merely reshape the future of galaxies. It reshapes the future of understanding. The observable universe is not the universe. It is only the portion reality still permits us to investigate. Beyond that boundary, existence continues without consultation, without communication, and eventually without consequence for anything that remains inside our horizon. There is something profoundly humbling about that distinction. For centuries, each expansion of human knowledge made the universe appear larger. Today, the same observations reveal another truth. No matter how successful science becomes, there will always exist a boundary where observation ends, not because curiosity failed, but because physics drew the line. That boundary is moving, not toward us in panic, not away from us in malice, simply onward, following equations that care nothing for memory, history, or expectation. One day, countless galaxies that now populate astronomical catalogs will exist only in archived observations made by civilizations that no longer exist themselves. Eventually, even those records may disappear. The galaxies will continue their evolution. Stars will still be born. Black holes will still merge. Planets will still orbit unseen suns. The universe will lose none of its complexity, only its witnesses. Perhaps the most unsettling of the cosmic horizon is not that the universe is becoming unreachable. It is that reality has never promised to remain knowable. For a brief moment, measured against billions of years, the history of the cosmos has opened itself to observation. We call that moment the present. There is no evidence that it lasts forever.